In this problem, we have an 80-kilogram crate that is simply standing on this moving cart on this inclined surface with a 15-degree angle with the horizon. And because the crate simply stands on the cart, it means that there's nothing else that keeps this crate from moving except for the frictional force between the surface of the crate and the cart. So we need to determine this acceleration. What is the maximum acceleration that the cart can have without causing the crate to move? It could be either tipping over or sliding relative to the cart. This is the same thing as asking what is the minimum acceleration A needed for the crate to start moving. We need to determine when that happens, when the motion happens, the relative motion of the crate with respect to the cart. Is the crate sliding relative to the cart, or is it tipping over? The static friction coefficient is given between the crate and the cart. So let's use this example to illustrate typically how we deal with this kind of problem. This is, by the way, a translation problem. There's no rotation or general plane motion involved. So we start with drawing a free body diagram of the crate. So the gravitational center is given, the dimension of the crate is given as well. It is subjected to weight, which is mg, and also the normal force from the cart. Right now, we do not know exactly where this location of the normal force is. And because the cart moves up, therefore the relative impending motion of the crate with respect to the cart is down. So this is the direction of relative motion of the cart. Therefore, the frictional force develops to prevent impending motion. Therefore, frictional force is up as well. So we need to determine the direction of the frictional force. That will greatly help with the analysis. You can tell that the frictional force is actually the only force that makes the crate to move uphill with the cart. If the frictional force is in the other direction, the crate will no doubt slide down. So now we have completed the free body diagram. Let's choose a coordinate system. Let's align our x and y coordinate system with the inclined surface and then perpendicular to it for convenience. And also we need to draw the kinetic diagram, which is basically drawing the MAG, which is in this direction along the inclined surface. This is the mass center or the gravitational center of the crate. So with this down, we can start writing our equations of motion. So let's write the first equation. Let's write resultant force along the y direction, which is again in this direction. And that equals to the normal force minus W times cosine 15 degree equals to 0. And this is n minus mg, which is 80 times 9.81 times cosine 15 degree equals to 0. Also, resultant force along the x direction, x is in this direction, equals to frictional force minus W sine 15 degree, which equals to frictional force minus 80 times 9.81 times sine 15 degree equals to MAG, which is 80 times 8G. So now here we have two equations, equation 1 and equation 2. Now how many unknowns do we have? We have normal force, frictional force, and AG. So we have 3 unknowns, only 2 equations, obviously not enough to solve for all of our unknowns, even though we can actually solve for normal force here. So from the first equation, we can find out that normal force equals to 758.1 Newton. So now, in order to solve for the other 2 unknowns, we need one additional equation. So where do we get that? We can write different third equation based on the assumption we make. So if we make the assumption that assume let's assume first sliding occurs. This is when the crate slides relative to the cart, so the crate will slide down in this direction. If that happens, we will know that the frictional force between the crate and the cart has now reached the maximum static friction, which now can be evaluated by this equation, mu s times m. You cannot use this equation unless you know that the static friction has reached the maximum value. This is when sliding is about to occur. So mu s is given as 0.5 times normal force, which is solved earlier, 758.1. So this is our third equation. So from here, we can solve for frictional force to be 379 Newton. It's actually not important because it's the Ag that we need. Ag can then be solved from this second equation by substituting frictional force into it. Then Ag equals to, in this case, 2.20 meter per second squared. This is not the final answer. This is the acceleration needed for sliding to occur. However, what if it's tipping over that occurs first? If that's the case, then frictional force no longer equals to mu s n. Remember, this equation can only be used when frictional force reaches limiting value when sliding is about to occur. So in this case, we cannot write this third equation. We need another third equation. Based on what we've learned back in statics, we know that when tipping over is about to occur, we actually know the location of normal force. Before, we wouldn't know the location of normal force, but now we know that the normal force location, it has to be placed at this corner. Let's call it point A. So with this specified location, now we can write our moment equation of motion. So if we summarize the moment about point G, which is the gravitational center, because we have translation, therefore the resultant moment about point G equals to 0. This is only true at point G. If you summarize the moment about any other point, the result is not 0. So this is only true for translation for moment about G, gravitational center. So in this case, if again we assume counterclockwise to be positive, then the frictional force is causing counterclockwise rotation with moment arm of 1.5 meter, and the normal force is causing clockwise rotation with a moment arm of 0.5 meter. And that equals to 0. And because we know what normal force is, from here we can solve for normal, so let me say that first. This is our third equation now. So now with 1, 2, and 3 equations, we can solve for frictional force to be 252.7 Newton. Similarly, substitute into the second equation, we can solve for Ag to be 0.60 meter, 62 meter per second squared. So again, this is the maximum acceleration the car can have without causing the crate to tip over. Before I further analyze the situations, let me say that you can actually write an alternative moment equation. You can summarize the moment about point A. This is not 0. However, the resultant moment about point A, which equals to the moment caused by the weight, if we take counterclockwise to be positive, then this equals to W times sine 15 degree times 1.5 minus W times cosine 15 degree times 0.5. So that's the x component and that's the y component causing moment about point A. Normal force and frictional force pass through point A. They do not have moment about point A. And this equals to not 0, but the kinetic moment mk about point A, which equals to the moment caused by the kinetic force mag about point A. Mag is causing clockwise rotation about point A. Therefore, this equals to negative m times ag times the moment arm of 1.5, because ag is placed at the gravitational center. Therefore, from this equation alone, actually, you can solve for ag, which will give you the same answer. So this is an alternative method. Either way, now we have evaluated two acceleration. One is the acceleration that will cause sliding to occur. The other is the acceleration that will cause tipping over to occur. And if we compare them, we realize that the second situation only takes a smaller acceleration. Therefore, the final answer should be ag equals to 0.62 meter per second squared. And this is when tipping over occurs, because it takes smaller acceleration to cause tipping over. It is easier to cause tipping over. It is harder to cause a relative sliding. So that's the final answer to this problem. So even after you have made the assumptions, have done the calculations, you still have to make a decision.